All right, so I'm going to go ahead and get started. So this is our learning objective, is that you know your product and quotient exponent laws and that you can apply them. This is going to be our lesson for today as well as tomorrow. So today's work will be on the product law and tomorrow's will be on the quotient law, but this one video is going to go through both of them. All right. So first I'm going to show you what the product rule is. Our product rule states that when we are multiplying exponents with the same base, and we know in this case our bases are m, which is our number being multiplied by this exponent m here and this exponent m here. When we are multiplying exponents with the same base, so in this case we share the base a, we would add the exponents. So a to the power of m times a to the power of n, we would add those exponents. So a to the power of m plus n, whatever those exponents are. So let's look at the examples they give us. If you look at the first one, you have x to the power of 3 times x to the power of 5, which would give you x to the power of 3 plus 5. And 3 plus 5 is 8. So same thing, you have 3 to the power of 2 times 3 to the power of 3. You have a matching base of 3. So it's going to be 3 to the power of that first exponent 2 plus that second exponent 3, and 2 plus 3 is 5. So let me show you why this works. So let's say we had 3 to the power of 5 times 3 to the power of 4. We know when we were creating our expanded form that 3 to the power of 5 is 3 times itself 5 times. And we know 3 to the power of 4 is 3 times itself 4 times. Well, if I were to count all of these 3's up, I know that I would have 4 and I would have 5. Because I have 9 3's in total that I'm multiplying, I know that it would be 3 to the 9, which is 3 to the 5 plus 4, because when I multiply them, because that is saying 3 times itself 9 times, we see all of those 9's here. When we were to draw it out in our expanded form, we know that that is why it works. So down here, again, we know that we have a matching base of 2. So our base of 2 to an exponent of 3 times 4. So I know when I'm multiplying like bases with different exponents, I can add. I know 3 plus 4 is 7. Well, so let's check that. I know 2 to the 3 is 2 times 2 times 2, 3 times. And same with 2 to the 4, 2 times itself, 4 times. If I were to count it out, I know that I have 1, 2, 3, 4, 5, 6, 7. So 2 to the 7, which is what we got when we added them, because it's the same as saying 2 times itself 7 times. So now that we see what it is and how it works, let's go through a couple of different example types. So on this first one, I have a to the power of 5 times a to the power of 6. So we have a matching base of a. So we know that we're going to have a to the first exponent, which is 5, plus the second exponent, which is 6. So a to the 5 plus 6 is going to leave me with a to the power of 11. Now we're going to look at that second example. I have b to the power of 3 times b to the power of 9. So we have a matching base of b. And we know when we have a matching base that we're multiplying, we would keep that matching base and we're going to add our exponents. So b to the 3 plus 9. And I know 3 plus 9 is going to give me 12. All right, now 3 looks a little bit different, but we are still doing the same thing. We multiply. When we are multiplying like bases, we are going to add the exponents and keep the matching base. Well, I'm doing the same thing. I just have 2 different bases. I have a base of A and I have a base of B. And just so that we can see it, I have a base of B here and a base of A here. So we are still just going to keep my matching base of A, and I have an A to the 3 plus, and I have an A to the 2, and then I have a matching base of B to the 2, plus I have a matching base B with a 3. So we can only combine them if they have the same base. So in this case, I have a base of A and a base of B. Those are different bases, so I cannot combine my A and my B, but I can combine my two A's and my two B's. And I know that A to the 3 plus 2 is going to leave me with A to the 5, and B to the 2 plus 3 is going to leave me with B to the 5. So my answer here would be A to the 5, B to the 5. And I write my A's funny. I write them like they type them. So this is an A though. So if this is A. Some people say my A's look like 2s, and some people say that they look funny. So just in case, so we're all clear, that's A to the 3 plus 2 and B to the 3 plus 2, giving me A to the 5, B to the 5. Because we can only combine them if they are the same. Well, so let's look at this next one. I have 3 A to the 7th times 2 A to the 4th. I have a lot of kids get thrown off by this. We are still multiplying our coefficients like normal. So I have a 3 times a 2. Those numbers they have no exponents, so you just multiply them like you would regular numbers. So I know 3 times 2 is going to give me 6, and then we are still just with our A, keeping that matching base and adding our exponent. So I have 6A to the 7 plus that second A to the 4, because that's our matching base. And when I combine it, we're going to keep our 6, and A to the 7 plus 4 is going to leave me with A to the 11. All right, and then I have one more different type of example. If you look at this one, I have my two numbers that I'm going to multiply like normal. I have 5 with no exponent and 4 with no exponent, so I can just multiply 5 and 4 like I regularly would. 5 times 4 is going to give me 20. And then I have C to the 5. I have no C's in my second part. So C to the 5 is just going to say C to the 5. There's nothing to combine it with. And then I would keep going to my different bases. So then I have D and E. So I have D to the 6th and D to the 4th. So I know that with my D, we're going to keep that matching base of D. And I'm trying to pick a different color, because we know C is the only one of itself. We'll circle this in black because we did our numbers in black, just so it's kind of color coordinated. C was the only one of its base, so we left it C to the 5th, and then we have base D, so circle that in red, and base D. So we're going to keep that matching D, and it's going to be D to the 6 plus, this one is a 4, and then our last base that I see, I have E. So I have E to the 2 and E to the 5. So then I have E to the 2 plus that E5. So plus the 5. So then we would go in and we would simplify our answer. I have 20 because my 5 times my 4. C to the 5 stays C to the 5. I have D to the 6 plus 4. Well, 6 plus 4 is 10. And then I have E to the 2 plus 5. So E to the 2 plus 5 is 7. And then I've simplified as much of it as I can. So now I paired these two together because our quotient and our product rule kind of go hand in hand. So when we are multiplying like bases with different exponents, we add, multiply, add, divide, subtract. So if we have a matching base, in this case a matching base of A, you would keep that matching base, and this time we are going to subtract our exponent. So I know a to the m over a to the n, you're going to subtract top minus bottom. So a to the top exponent minus the bottom exponent, and you're going to keep that matching base. So when dividing exponents, and that's basically what I said, exponents with the same base, you're subtracting those exponents. So here's our example. Our matching base is x. So we're going to keep that matching base of x, and you're going to subtract your exponent. So top one, 4, minus bottom one, 2. So I'm going to have x to the 4 minus 2. And 4 minus 2 is 2, so it'll simply be x to the 2. And then same thing here. I have a matching base of 3. So I know I'm going to keep that matching base of 3, and I'm going to say top exponent, which is 5, minus bottom exponent, which is 2. So 3 to the 5 minus 2, and 5 minus 2 is 3. So again, like before, I'm going to show you why this works. So we know when we were doing our expanded form that 2 to the power of 5 means 2 times itself 5 times. So I have 1, 2, 3, 4, 5 2's here. And 2 to the power of 3 is 2 times itself 3 times. So 2 times itself 3 times. Well, when we are doing this, we subtract. I know that if I have a pizza, so let's look at these two real quick. So I have 2 over 2. I know that if I have a pizza and cut it in half, if I have both halves, I have one whole pizza. So, same thing with these. If I have 2 over 2, this would simply, these would simply equal 1. Again, 2 over 2, I have both parts of the whole. 2 over 2, I have both parts of the whole, and I am left with 2 times itself. So base of 2, the number being multiplied by itself, and I have it times itself. I have 2 of them, so 2 to the power of 2. So let's check it now. So we know that our quotient rule says we keep that matching base and we subtract our exponent. So 5 minus 3. We know that 5 minus 3 is 2. So we know that our drawing it out does actually work. We see it happening. So let's look at this next one. Showing how it works one more time, and then we'll go ahead and do some without drawing it out. So we know 3 to the power of 4 is 3 times itself. 1, 2, 3, 4 times. And we know that 3 to the 3 is 3 times itself. 1, 2, 3 times here. So I'm going to go ahead and I'm just going to erase that because I was just trying to emphasize that you knew where we were looking. All right, so then I know that if I have, so let's look at it again. I have 3 over 3 here. I know if I have a pizza and I have all 3 parts, 3/3, I have one whole pizza. So again, like before, 3 over 3 is just 1. 3 over 3 is just 1. And 3 over 3 is just 1. So I am left with 3 being multiplied. I only have 1 3. And we already learned our one rule, our one rule states that anything to the power of 1 is just itself. So 3 to the power of 1 is simply that 3 we had left. So let's go back and check our work. We know that with matching bases, we can keep the matching base. We can say top exponent minus bottom exponent. 4 minus 3 is 1, so we get 3 to the 1. And again, like we said, our one exponent rule states that anything to the power of 1 is simply itself. So 3 to the power of 1 is just 3. So that is why it works. So let's go ahead. We'll go ahead and look at a couple of different types of examples. So first, right off the bat, I have b to the power of 9, and this line right here is one of the things I have to repeat and repeat and repeat. When we see something over something else, this line means that we are dividing. So when I have b to the 9 over b to the 3, I know that I'm dividing those. So we have a matching base of b, so we can keep our matching base. We can say top exponent minus bottom exponent. So b to the 9 minus 3. Well, I know that 9 minus 3 is 6. So b to the 9 divided by b to the 3 is simply b to the 6. Let's try another one. So I have k to the 7 over k to the 4. A matching base is k, top exponent minus bottom exponent. So k to the 7 minus 4, and 7 minus 4 is 3. So we're just left with k to the 3. All right, and looking at this next example, I'm going to say the same thing I said with our product rule. This works for matching bases. So I can do my keep common base and subtract only for my bases that are the same. So I have a base of k and I have a base of d. So I know my matching base k, we're going to keep that k and say top minus bottom. So 7 minus 5. And then we're going to keep that matching base of d, and again, top minus bottom, so 6 minus 2. And when we combine all that, we know k to the 7 minus 5. Well, 7 minus 5 is 2. And again, d to the 6 minus 2. Well, we know 6 minus 2 is 4. So we are left with k to the 2, d to the power of 4. All right, so let's look at another example. I tried to come up with as many different kinds of these problems as I could think of. So I have another one. What I notice about this is that I have two different bases. But if you look, I have a base of q at the top, but not at the bottom. And down here, and let me switch colors, I have a base of L and a base of L. Well, we know that when we are subtracting, we're subtracting because we're moving these up. So, q to the 6, we could say any whole number because a top, so if I have 5 and I wanted to make the fraction, I know that I can put it over 1. So if I have q to the 6 and I want to make it a fraction, over 1. So we know that q to the 6 is just our whole number. So I have L to the 12 over L to the 7. So I know I'm going to keep that matching base of L and put it to the 12 minus 7. And q over 1 is just q. So L to the 12 minus 7. Q stays the same because there's nothing to get rid of underneath it. It's just a whole number over 1. So a whole number is a whole number. This whole thing is over an assumed 1. That's just the invisible math of it. So, because what we're doing when we're subtracting that 7 is that this also becomes a 1. There's a whole invisible 1 under all of it. So I know L to the 12 minus 7 is just L. Keep that matching base. 12 minus 7 is 5. And Q to the 6 stays Q to the 6th. All right, so look at this next one. I have regular numbers with no exponents, and then I have R's, a base of R. So like we did with multiplication, when we have numbers with no exponents, we can still just divide those like we regularly would. And I know 21 divided by 7 leaves me with 3. And I know R to the 11 over R to the 9, we're going to keep that matching base. So circle it so I can switch my colors. Keep that matching base of R. Top exponent minus bottom exponent. So then we're left with 3 to the r, and 11 minus 9 is 2. And I'm going to pause and jump back to here. Anything divided by 1, because we know this line means division, is itself. So this bottom, once we're canceling out, is like q to the 6 divided by 1 is still just, it's q to the 6. All right, so then, all right, sorry, I just tried to sidetrack, so I made sure I covered everything about that one. So I'm going to erase this 3, just so it's out of my way for 6. So I know I have r to the 4 over r to the 2 d to the 6. What I wanted to point out with this one, so let's do our r real quick like we regularly would. So I know I'm going to keep that matching r to the top exponent minus bottom exponent, and r to the 4 minus 2 is just r to the 2. What I wanted to show you with this one is that later on in these exponent rules, excuse me, I don't know why it switched on us. Later on with these exponent rules, we will deal with changing and switching negative exponents. Right now, if you see something like this, I want you to, and you do not have a d on the top, if we move this up, the sign switches to negative, and we have not yet covered negative exponents. So for right now, I would want you to subtract that matching exponent of r and keep that d to the 6 at the bottom. And I'm going to star it because when we get to negative exponents, I'll show you what you would do to this d to the 6 at the bottom. We're not going to move it because it would change the sign of the exponent, and we do not know how to yet do that. So I only wanted to show you this to show you that if you have it on the bottom, we're going to leave it alone until we learn about the signs of these exponents. And we'll learn about that further as we get through our exponent laws. So today we talked about our product and our quotient exponent laws. What our product law told us was that if we have a matching base, we keep that matching base. So x, and you add, and I wrote it as division. Talking about product rule, writes division. Silly Miss H. All right, so I have x to the power of 2 times x to the power of 2. When we are multiplying like bases, you keep that matching base, in this case x, and add your exponent. So x to the 2 plus 2 gives us x to the 4, and we can only combine them if they have matching bases. And then, so with our quotient, which is division, we know product means multiplication, and quotient means division. That's why it's the product and quotient laws. We know that x, so x to the 5 over x to the 2. We know that we're going to still keep that matching base, and we can only do this if the base is the same. X to the top minus the bottom. So we're going to be left with x to the power of 3. So that was our learning objective today. We looked at the product exponent rule. We looked at the quotient exponent rule, and we looked at a couple of different ways you might see it. So if you're still having issues with this, we are going to be covering it in our small group today and tomorrow. Today, the product assignment is due on Schoology, and tomorrow, the quotient assignment will be due on Schoology. All right, guys, have a great day. Goodbye.